Hello, my name is Kirill Simonov, and I'm going to talk about FunSQL, a library for constructing SQL queries. What is SQL? Why you may need to construct it? And does this really require a dedicated library? SQL is a specialized programming language used for querying database systems. If we want to fetch some data from a database, we create an appropriate SQL query and submit it to the database server. If a Julia program needs to fetch data from the database, it means that the SQL query should be submitted by Julia code. From the perspective of a Julia programmer, a SQL query is just an opaque string value. However, when you use SQL in a program, it's rare that the whole query is given to you in advance. More often, the query will depend on the user input, like in this form. This means that the query is no longer a constant value and instead must be constructed on the fly. This can be done by generating individual fragments of the query as strings and concatenating the fragments to assemble the target query. Now imagine that the user, encouraged by your tremendous success, asks you to improve this form. Make it like this. This form requires you to combine data from multiple database tables in order to build a complicated criteria on patient records. Can you do it by concatenating string fragments? Yes, you can, but it will be challenging, error-prone, and definitely not fun. Clearly, a more systematic approach is necessary. I'm going to explain how a FunSQL library lets us dynamically build complex queries that could drive forms like this one. For this form, we need to use filtering and join operations, correlated subqueries, and aggregate functions, which are going to be the topics of my talk. I will assume that you are familiar with SQL and will not explain the semantics of particular SQL operations. However, I'll describe how FunSQL query objects are translated into SQL, especially when this translation is not straightforward. In many cases, FunSQL significantly deviates from the lexical structure of SQL, and I'm going to justify it by demonstrating how it makes query construction more composable. Before we proceed, I need to make a small diversion to introduce the database schema that we are going to use in our examples. We use a fragment of the so-called AMOP Common Data Model, an open-source database schema used in healthcare for observational research. As typical in healthcare, this schema is patient-centric. The person table stores information about patients, including basic demographic data. Patient addresses are stored in a separate table called location. The bulk of patient data consists of clinical events, encounters with healthcare providers, recorded observations, diagnosed conditions, prescribed medications, etc. In our examples, we will only use two types of events: visits and conditions. Before we start constructing queries with FunSQL, we need to describe the database schema in FunSQL terms. For each table in the database, person, location, visit occurrence, and condition occurrence, we define a corresponding SQL table object, which encapsulates the name of the table and the list of available columns. Now we'll take a SQL query and show how to reconstruct it using FunSQL. Any SQL query starts with a from clause, where we choose the starting table. In FunSQL, we start building the query object with a from constructor, which takes as a parameter a SQL table object. What follows is a sequence of clauses, such as where, which transform the table data to the desired form. FunSQL provides constructors to express SQL clauses and let you compose them using the chain operator. A SQL query is concluded with a select clause, which is performed the last, but is always written at the top of the query. In FunSQL, select respects the actual order of operations. Moreover, in FunSQL, select is optional. If it is not present, all columns from the starting table will be selected. Finally, once the query object is constructed, it can be rendered to generate a string value containing the SQL query. When you assemble a query object, you may need to reference a column of a table. FunSQL provides two ways to do it: bound references and unbound references. A column reference can be created by taking an attribute of a query object. This reference is resolved against this particular query. An unbound reference is created as an attribute of a special object called get. Such references are resolved dynamically at the place of use. Which one do you want to use? This really depends on your circumstances. Bound references make it easy to disambiguate columns of different tables. On the other hand, unbound references help to make query composition more modular by letting you build expressions independently from the base query. To build query objects, you also need to generate SQL functions and operators. In FunSQL, functions and operators are created as attributes of the object fun. Certain SQL functions, in particular comparison operators, can also be created using the standard Julia broadcasting syntax. Aggregate functions, such as count and average, have their own namespace object, egg. Now let me quickly introduce the join clause. In SQL, join is used to correlate the output of two queries. In this particular example, we join two tables, person and location, to relate each patient record to the corresponding address. As you can see, FunSQL notation for join mirrors the syntax for join in SQL. However, there is one feature in this example which is unique to the FunSQL notation. It's the use of hierarchical references. The join clause in FunSQL can introduce ambiguity to the use of unbound references. In this example, both tables, person and location, have a column called location ID. So in the context of the join, if we use an unbound reference getLocationID, which table it refers to? We like the convenience of unbound references, and we would like to keep them useful even in the presence of ambiguous column names. For this purpose, FunSQL allows arranging available references in hierarchical namespaces. A namespace is introduced using the Julia pair notation and can be traversed by taking a sequence of attributes of the get object. This way, we can place the location table into its own namespace, making the reference to location ID unambiguous. Let me show you another example to demonstrate how a logic query could be incrementally constructed from independent components. In this example, we ask to find patients that satisfy two conditions, on their age and on their place of residence. We can implement these constraints independently. Build two queries, one which finds age-eligible patients and the other that restricts locations to Illinois. To apply both constraints at the same time, we combine these queries using join. Although this is very straightforward, it may still surprise you. If you are familiar with SQL, you may notice that the final query seemingly violates the lexical restrictions of the SQL grammar. Indeed, SQL clauses must be applied in a particular order. In this example, from followed by where followed by join is actually a syntax error in SQL. I should clarify that in this case, we could simply switch these two clauses without changing the expected output of the query, but it's not necessarily possible in general case. On the other hand, FunSQL doesn't have this restriction. Query constructors can be applied in any order, as required by the query logic. However, it should still surprise you. After all, any FunSQL query object is ultimately rendered into SQL, so how could possibly FunSQL ignore the lexical restrictions of the SQL grammar? SQL grammar enforces a strict order of SQL clauses. A SQL query starts with a from clause, followed by a series of joins, followed by where, group by, etc. A query is concluded with a select clause. But SQL grammar also allows us to restart the query construction by placing a complete SQL query inside a fresh from clause. At this point, we could again apply joins, where, group by, and so on. This property of SQL grammar is what FunSQL uses to let you apply query constructors in arbitrary order. Here is how it works. Each query constructor is translated not just to the corresponding SQL clause, but to a complete SQL subquery containing this clause. Composition of query constructors is not a concatenation of SQL clauses, but in fact a composition of SQL subqueries. This is how FunSQL could bypass the restrictions on the order of SQL clauses. You could say that FunSQL presents SQL as an algebra of queries. In this algebra, from becomes an elementary query, where and select unary query operators, and join becomes a binary query operator. This diagram shows how query composition works in practice. This particular FunSQL query is composed out of 6 constructors, which together are converted to 6 nested SQL queries. You should have noticed that these SQL queries are not complete. The select lists are missing. They have to be deferred until FunSQL can observe the final select, then all the nested select lists are populated automatically. Finally, this is a complete SQL query. But I should mention that FunSQL will merge two nested SQL subqueries if it can prove that it does not violate the SQL grammar. In this example, the pairs of from and where, as well as join and select, will be eventually merged together. I explained how FunSQL query constructors do not directly reflect the SQL syntax. But FunSQL also provides a separate set of constructors to represent the lexical structure of SQL, the syntax of a SQL query. This representation serves as an intermediate layer between the FunSQL query objects and the actual SQL. FunSQL users rarely need to interact with this layer directly, but it may be necessary in order to customize serialization of SQL functions with a regular syntax. And this is the final form of the SQL query, which will be generated from this query object. As I explained, FunSQL takes control over managing intermediate SQL subqueries. But SQL subqueries have an additional function, creating intermediate values. For this purpose, FunSQL provides a constructor called define. Define is used to create a new calculated column. Just like with regular columns, we could fetch the column value by using a bound or an unbound reference. To calculate the column, define will create a separate SQL subquery. However, it will only happen if the column is actually used in the query. It means that you can define all the calculated columns that you may potentially need without incurring unnecessary performance cost. FunSQL lets us build queries from components developed separately and assembled together on the fly. This is a powerful technique, but it makes debugging more complicated. To alleviate this problem, FunSQL provides a way to inspect a constructed query object. When the query is displayed in REPL, or when you directly use the display function, FunSQL will serialize the query object as a Julia expression. In general, a query object can be an arbitrary acyclic graph and therefore cannot be constructed without use of variables. For this reason, FunSQL serializes a query object as a let expression, assigning a variable to each intermediate query node. The same representation is displayed when FunSQL raises any exceptions. This really improves development and debugging experience with FunSQL. We covered the fundamentals of FunSQL. Next, I will talk about correlated subqueries in SQL and FunSQL. But before we discuss correlated subqueries, let me quickly introduce query parameters. A SQL expression may include a reference to a query parameter. When we execute the query, we must supply the actual values for all the parameters used in the query. This is a restricted form of dynamic query construction directly supported by the SQL syntax. FunSQL can construct queries with parameters. A parameter is created as an attribute of the object var. FunSQL also provides an interface to prepare parameter values for execution. Now let's discuss correlated subqueries. The SQL query in this example contains two subqueries, the outer subquery that loads the person table and the inner subquery which loads the condition occurrence table. The inner subquery is called correlated because it includes a reference to the column person ID, which is provided by the outer subquery. How to reproduce this query in FunSQL? We could try to follow the SQL syntax, build queries for loading person and condition occurrence tables, then add the correlated condition, and finally combine outer and inner queries. However, FunSQL is going to complain about the use of the reference to the outer subquery in the context of the correlated inner subquery. Why is that, and how can we deal with this problem? The fact is that a correlated subquery is not, despite what the name suggests, a query. If by query we mean something that we could execute against the database and get back some result. Indeed, the result of the correlated subquery depends on the value provided by the outer subquery, and can only be generated if we know this value. In other words, a correlated subquery is a query-valued function. FunSQL notation for correlated subqueries deviates from SQL syntax and instead follows the notation used in the majority of programming languages. Specifically, FunSQL introduces formal parameters, which can be used in the body of the correlated query and must be bound to the actual values at the invocation site. In FunSQL, formal parameters of a correlated subquery use the same notation as global query parameters. They are created as attributes of the object var. Binding parameters to values is done explicitly using the bind constructor. We find it very convenient to wrap creation of a correlated query in a regular Julia function. Then the invocation of the Julia function gives you back an object which represents invocation of a SQL query function. This function can be used to create a standalone query object if it is called with the literal value. This can be used to independently test the correlated query. When it is called with an arbitrary SQL expression, in the context of the outer query, it generates a proper correlated query. Our last topic is dedicated to aggregate and window functions. In SQL, we use so-called aggregate functions to summarize data over a group of rows. First, we must apply the group by clause to partition the dataset into disjoint groups. Then we could use aggregate functions, which produce one value per group. In this example, we use count, which simply counts the number of rows in each group. As you can see, FunSQL notation for group constructor and aggregate functions reflect the SQL syntax. Note that in FunSQL, aggregate functions are separate from regular functions and have their own namespace object, agg. There is one case where FunSQL notation differs from SQL, when we apply an aggregate function to the dataset as a whole. In this case, in SQL, we omit the group by clause. In FunSQL, the group constructor is mandatory. In the next example, an aggregate function is used in a condition to filter out certain groups. SQL provides a special clause for this purpose, called having. The reason why SQL needs another filtering clause is that the standard filtering clause, where, is applied before group by and therefore cannot be used with aggregate functions. On the other hand, FunSQL allows where to follow the group constructor so that it can freely use aggregate functions. In fact, FunSQL has no lexical limitations on the use of aggregate functions. While in SQL, aggregate functions can only be used in the select or having clauses, there is no such restrictions in FunSQL. They could be used in any context where an ordinary expression is permitted. The only requirement is that for each aggregate function, FunSQL can determine the associated group constructor. Here is how it works. Each group constructor is converted to a SQL subquery with a group by clause. FunSQL will collect all aggregate functions associated with this group constructor and place them into this query as a part of the select clause. In this example, an aggregate function max is used as an argument of the where constructor. FunSQL appends max to the select clause of the group by subquery and uses an alias in place of the aggregate function within the where clause. In a way, the relationship between the group constructor and aggregate functions is the same as the relationship between from and column references. In this particular case, FunSQL could merge all three subqueries into a single query with group by and having clauses. In general, it is not always possible, but in any case, such transformation does not affect the output of the query. Close relatives of aggregate functions are window functions. Where aggregate functions are used for summarizing a dataset, window functions let us relate different rows of the dataset to each other. Support for window functions, available options, and syntax vary between different SQL implementations. The FunSQL notation for window functions is modeled after SQL syntax with an explicit window clause, where the window specification is declared in a separate clause and has a name assigned to it. In FunSQL, this role is performed by the partition constructor. Once partition is applied, a window function is created using the notation for aggregate functions by taking an attribute of the namespace object agg. In this example, we use a window function to find the gap between adjacent visits. I should clarify that this query assumes that there are no overlapping visits, otherwise we may get a negative value for the gap. It may come as a surprise that both aggregate and window functions in FunSQL use the same notation. The only way we could differentiate them is by finding the associated constructor, group or partition. There is a reason for that. Let's review how group and partition operate. Group creates a new dataset consisting of all unique values of the group key and associates with each output row a collection of the corresponding elements from the input dataset. Partition does not change the dataset, but instead associates with each row a collection of related rows according to the window specification. In a way, we could think of partition as a cumulative group operator. In both cases, we get a dataset where each row has a collection of other elements associated with it. The aggregate function acts on this collection without regards as to how it was generated, whether by group or by partition, and the produced result matches a regular aggregate function or a window function. That's the reason why we use the same notation for both. To demonstrate that FunSQL notation for aggregate and window functions is suitable for building complex queries, I'm going to show the next example, where we need to merge overlapping intervals into a single encompassing period. It is a common task for patient-oriented queries, where we may need to determine the periods of continuous observations, medication exposure, etc. Although it's a simple exercise in a regular programming language, it could be a challenging problem to implement this transformation in SQL. We will solve this problem in several steps. First, we will take the intervals that start a new period. These are the intervals for which the distance to the previous period is positive. Once the starting intervals are designated, we can determine all the other intervals that belong to the same overlapping period. This can be done by calculating the cumulative sum, which transforms an indicator to a staircase function. Once we have a value which unambiguously identify intervals that belong to the same period, we can finally merge them by applying group by. The boundaries of the period could be calculated using the mean and max aggregates. What perhaps is the most important lesson of this exercise is that once this transformation is constructed, it could be encapsulated to effectively create a new query operator. This is the level of abstraction which is not available in plain SQL. I hope I was able to demonstrate the essence of OneSQL, expose the full power of SQL in a uniform algebraic interface while shielding the user from irritating but inconsequential SQL quirks. At this point, I could show you how to implement the form that I demonstrated at the beginning of the talk. We start by delegating the query construction to a separate function. This function itself assembles the query from high-level components combined together using the chain operator. All the components can be easily implemented using the notation covered in this talk. We use a simple join to implement the filter by state. The filter by condition could be implemented using a correlated subquery. Finally, the date of the latest visit can be found by applying an aggregate function. Of course, this is not the only possible solution, and depending on the database engine, the size of the dataset, and available indexes, you may need to adjust the generated query. In a conclusion, I'd like to say a few words about the current state of OneSQL and the plans for the future. OneSQL is a relatively young project, approximately 4 months old. It was started as an intermediate layer between SQL and a high-level combinator-based query interface, but soon it became an independent project. The name OneSQL was chosen to suggest that it makes dynamic SQL construction fun by automating all related non-fun activities. On this slide, I listed the features of SQL which are already supported, as well as the to-do list ordered by priority. Although there are still many gaps in our coverage of SQL features, the implementation is robust enough so that I could recommend using OneSQL as long as it provides the features that you actually need. We used OneSQL with 3 database backends: Postgres, Amazon Redshift, and Microsoft SQL Server. Our initial focus was on the data retrieval capabilities of SQL. We want to expose all semantically meaningful features of the select statement while normalizing the differences between SQL dialects as much as possible. Eventually, we want to support data manipulation and data definition capabilities as well. The documentation is still lacking, but you could look for inspiration at one of our publicly available projects, Odyssey Cohort Expressions.gl, which is an independent MIT licensed implementation of the Odyssey Cohort Definition Standard. If you have any questions, suggestions, bug reports, or just a fresh pun with the word fun, please contact us on Zulip or through GitHub. We would love to hear about your experience with SQL and OneSQL.